So in last lecture, we have been studying about generalizations on the dividers and impulse voltage measurements, layout, etc. We have studied. We will go through briefly and then proceed further. It is continuation of the last lecture only. So this was the layout of measuring system that was explained in the last lecture. So the voltage measuring system consists of this region. So just to recall, so it involves this resistor R2, damping resistor, and then this connecting lead, and then this divider, and after that this signal cable or measuring cable, and then to oscilloscope. So this is the basic schematic diagram of a potential divider for impulse voltage measurements. Again, here you can see it starts from damping resistor, and then this we have seen. Different types of dividers are used that we will cover soon. And sources of errors were discussed, the stray capacitances, etc., impedance error, and parasitic oscillations were introduced. Now, this was the low voltage impulse divider for measurement, less than 100 kilovolts. In the range of 50 to 80 kilovolts, they are available. So in this case, this was a single unit resistor. Again, this is single unit resistor, and compensation can be done for this by using capacitor C1 and Cm. Which can be varied to adjust in such a way that R1 by R2 equal to Cm by C1, so that it becomes independent of the frequency. This was discussed in the last class. Now let us look into the transfer characteristics of measuring system. So the need for this understanding is essential because for high voltage dividers, actually, if you consider resistive divider, it is a series combination of several resistors, and the test object is will be very big, and then in size, I'm telling, and then connecting lead also very high above the ground, and then the system actually forms a transmission line that we will cover after some time. So before studying, in detail, now a 4-terminal representation of the measuring system is given here. So the VI, this input, is the voltage across the test object, and V0 is the output at the recording instrument. This one is at the recording instrument. And of course, A is the matrix which determines the transfer characteristics of the system, measuring system, which includes the damping resistor, the lead, connecting lead, the divider, and then signal cable, everything. So that is the system, complete system. Now, frequency response analysis can be done for this. Actually, so suppose, have you heard of frequency response of any system? Harshit?
Border plot and accurate, heard that.
So frequency response consists of, a magnitude plot and a phase plot, and a transfer function can be determined from that, So here also similarly, so this is the voltage across the test object, and this is the output voltage. So to obtain the frequency response, what we need to do?
We have to change it into frequency domain, sir, and then plot the phase.
Negative
We
was
first have
the
to find the
constant.
transfer function and then we have to convert it into the Laplace transform and then we having the frequency response after putting s equal to j omega.
Okay, so fundamentally, we have to study what is the response of the system at different frequencies, right?
Yes,
Suppose,
sir.
as an example, any input, a sinusoidal function can be given, and then output can be measured at different frequencies, and then you can get a magnitude plot and phase plot, from which the transfer function h j omega can be obtained like this. This is output function, this is input, and in frequency domain, so this becomes the magnitude of the transfer function, and this is the phase angle of the transfer function. So this is how it can be obtained. Of course, for high voltages, how to obtain this? There are difficulties, right? High voltages and input output ratio is very high, right? So how to get this one, and then an input source with variable frequency? It's a cumbersome process, but still we will see what this can be done. So after getting the frequency response, after getting the transfer function, now for any function, for example, any input function, we can obtain the output function. Simply convolve the input with the transfer function, get the output. Okay, and then directly after obtaining the output and input can be compared, and then errors can be evaluated. This is for AC and DC. DC also ripple voltages will be there. Therefore, the measurement is not constant. So it also depends on the transfer function and so frequency response. So we can compare the output and then input, and then errors can be evaluated. But for impulse voltages, this is it is a single shot event, as already told. And input is also not often known to us. And from output, you cannot say what the input is, right? Because already the output is, after convolution with the transfer function, it will come out. So some information is lost. So in practice, the input voltage Vi of t is not known, as only VO of t can be measured at the output terminals. And then how to assess? No appreciable transmission errors could occur if at least the amplitude frequency response h of omega is equal to mod of h of j omega would be nearly constant within a frequency range of interest. What it means is, if you have in a particular frequency range in which you are interested, if there is the amplitude of the function, transfer function, is almost constant, and then after that frequency range, then it suddenly falls or whatever happens. In this range of interest, if it is transfer function is magnitude is almost constant for different frequencies, then there will be no appreciable errors in transmission or in the due to transfer function. So this is one of understanding about the transfer function. Now, therefore, the spectra of an estimated input quantity is a tool to judge the necessary frequency range or bandwidth. Okay, this therefore, the spectra of an estimated input. Suppose you know the input quantity, certain input quantity, then you judge its frequency range. So if in its frequency range, if your transfer function has almost constant value, then obviously there will be no errors. Are you getting any echo?
No, sir, it's fine.
Okay. So this is the way to assess. Now, what are the types of inputs you are expect, and what do you expect? Which input is severe? Severe means which has high frequency contents, and therefore you should consider that its its magnitude may be in error, or its phase may be in error. So, which waveforms are you expecting for measure, and which will be severe among them as far as frequencies are concerned? Any answer? Poonam.
So
Which
impulse
type
function.
of waveforms do we
So
expect, and
impulse.
which is severe among them?
So impulse would be
Impulse would be severe. It is
yes, sir.
expected to have wide range of frequencies, right? So
Yes,
among the
sir.
impulse also, chopped impulse you have heard of, right? We have I have told you when impulse voltages
Yes, sir.
were introduced. So chopped impulse is expected to have wide range of frequencies. So therefore, we consider so the highest demands upon the measuring system transfer functions are imposed by impulse voltages, that to chopped impulse voltages. Now a chopped impulse voltage can be defined like this ideally. You can see its value is 0 for t less than 0 and t greater than tc also. So this is how it is. For t greater than tc it is 0 and t less than 0 also it is 0. So let us take this as tc, and this is 0, this is time axis t, and this is the magnitude, then vi of t if it is plotted. So t less than 0 it is 0, there will be nothing, and t more than 0 also, t more than tc also it is 0 again. So in between it follows this double exponential wave that we have studied earlier, right? Suppose if it is on the tail side, so it is like this, right? On the other hand, if it is on the front side chopped, see here, I have not put any oscillations because this is ideal assumption that after TC there will be nothing. It is 0. Now, if it is on front side, you can see a waveform like this, like a triangle almost. If it is chopped on front side, T, this is 0, this is Vi of T. So do you remember? So these are the different waveforms that are important as far as frequency range are considered. Now, let us look into the frequency response of these things. So even you can plot the frequency response using FFT in MATLAB or DFT in MATLAB. You can take a standard impulse function given by this double exponential function of approximately 1.2 by 50 microseconds, and then you chop it at different times and then find its FFT. Then you can observe. So these are the typical magnitude responses. This is Vi j omega mod magnitude. So this is frequency axis in megahertz, you can see. Now this is for TC is equal to infinity, means it is a standard impulse function. So you can see after about 0.5 megahertz, there is nothing, it's almost flat 0. So no frequency components are there in this full impulse wave. Full impulse wave means not chopped. The impulse wave which is not chopped. But you can observe here Of course, this is normalized frequency response for all other chopped waves. Normalized frequency response means this is made unity. Means at DC, this is almost DC, right? So at DC, all magnitudes are equated. Equated means by multiplying by appropriate factors, so that we can make the comparison here. So now you can see TC equals to 4 microseconds, TC equals 0.5 microseconds, TC equals to 0.1 microseconds. Of these, which are the waveforms corresponding to chopping in the front region?
So TC at 0.1 microseconds and 0.5
0.5
microseconds.
microseconds.
Yeah, these two, because this is standard impulse function 1.2 by 50 microseconds. Therefore, these two correspond to chopping in the front region. And this one corresponds to chopping in the tail region. Right? Now, you can see which are having higher demand on the frequency range. So obviously, if you are chopping in the beginning of the waveform or in the front region of the waveform, the smaller the time period, then you will have the larger the frequency content or harmonic content. So it goes on increasing, right? So, and if you chop in the tail region, so you can see the requirement on the frequency is this much only for 4 microseconds it is. So have you heard of bandwidth?
Yes, sir.
So lower
What it is?
frequency minus lower, higher frequency minus lower frequency. Range.
Huh?
Higher frequency minus lower frequency range.
The range of frequencies which will pass
The
through
range
the system.
Yes.
Yeah, actually, it is defined as some until certain magnitude. You expect the magnitude to fall by certain percentage only in that. So that is the frequency range corresponding to that is defined as bandwidth, right? Now let us see the 3 decibel bandwidth. 3 decibel band means minus 3 decibel band. So within that. Only minus 3 decibels, the magnitude will fall. So, for a full lightning impulse, harmonic contents becomes very small and hence it would not, in general, provide significant errors. The bandwidth has to be about 5 to 10 megahertz. See, this is the signal. This is the signal for full wave. Means TC equal to infinity, means chopping at infinite time. So that's what it means. It is full, and you can see after about 0.5 megahertz, the signal is almost constant. There is nothing. So roughly around 5 to 10 megahertz, if you define as the bandwidth, then until this, if you can pass the frequencies, then the signal will not have any attenuation or any errors. So very less errors are expected if you have such kind of bandwidth. Otherwise, if you look at the voltages chopped within the front, however, will require a very wide bandwidth. As you can see, which cannot be in general achieved with a measuring system for high voltages. That is the difficulty actually. You can see the voltage which is chopped at 0.1 microseconds. Even here, this is 10. Maybe next it is 100. So it should be more than this, right? You should not lose any frequencies. So it should be more than this. So that level of frequencies obtaining with high voltage systems becomes difficult. That's what is implied here. Now this is about frequency analysis. It has some certain difficulty. So therefore, the time domain method has come in picture. The frequency domain method is not only cumbersome, its application is cumbersome. You have to, for example, if you were to find out this transfer function by applying voltages of different frequencies and then finding out their magnitudes and all, So we need actually two quantities, modulus and phase angle, are necessary to measure the system transfer function, to obtain the transfer function. And for HV measuring systems, the evaluation by means of experimental unit step response is considered most suitable actually. So why unit step response has come into picture? Due to this cumbersome process and then difficulty in finding knowing the input in this case. So these are all the problems which hindered the application of frequency domain methods. Because what we have used previously, the chopped waveform is a theoretical waveform, and then we studied this is our frequency requirement and all. But we do not know what is actually the voltage that is applied at the terminals of the test object that is generated by an impulse generator. So how to know what are the frequency components of that? Because the practical waveform, experimental waveform, do not exactly follow does not exactly follow the double exponential function, right? Therefore, there may be some certain frequency components or certain deviations resulting from impulse circuit or load capacitance may be different, and then a little bit modifications might have occurred. That kind of things are not possible to know in advance. Of course, you will get a measured signal, but from measured signal, how do you get an input signal? It's not possible. So that is why there are some limitations for frequency response methods. Now, actually, standards specify the unit step response. This experimental unit step response. First, we will understand theoretically what it is, and then experimentally how to get the unit step response. Of course, there are again some limitations, but it is a better method, time domain method. Let us see that one. Output for any input signal using step response. Now, this is the unit input for a step function. Suppose, assume that we give that wherever Vi is there, input. What was the input? Where exactly the location is? That 4-terminal network.
Across the test object.
Across the test object. So, if we are giving a step input at that place, the step input is like this, right? So, Vi of t equals to 0 for t less than 0, and it is equals to some constant value Vmi for t greater than 0. This is the step function. So here it is given, the step function is given here. This is the step input function. Okay. Now for this, we will get a response like this. This is the unit step response. Of course, here there is a delay indicated here because actually it acts like a transmission line, and then there is always a delay from when the signal actually starts appearing on the oscilloscope. So this delay tau of dE, it is written here. Now, if the step response is g of t, suppose the step response is given by g of t. This is the function g of t. So this is what I have drawn, this oscillatory response. So this is capital G of t. Okay. If that is known, suppose we have applied it input means at the test object location, if we applied a step input, and then we measured at the oscilloscope this G of t, whatever it is. Then, if we know that, how to obtain the response for any arbitrary signal, V of I, is given by Duhamel's integral. So, if the step response is G of t, then V output for any input, arbitrary input Vi, is given by Duhamel's integral. So this is the two ways we can use that Duhamel's integral. This is one and this is another. Have you heard of convolution?
Yes, sir.
So is there any
No, sir.
similarity here to convolution?
Yes, sir.
Yes, sir. Area under.
Second.
Yes, sir. Area under one curve is being convoluted with another.
Okay, now you can see, suppose this integral, if you can see, this is Vi of t, and what is this actually? G dash t minus tau. G dash means
Differentiation of the
Differentiation of the
differentiation of G. So differentiation of step response is what?
impulse response.
Impulse response.
impulse.
So indirectly, what this integral is yielding, input is convolved with a impulse response. Okay, when input is convolved with an impulse response, what you will expect?
First impulse response at tau.
At t equal to tau.
Equals to
The
Tau.
At
output
t
of the
equal to tau, we get an impulse response again.
no. When this is impulse response, G dash t minus tau is the impulse response. T is equal to tau. No, tau is changing from 0 to t, right? Tau is
Yes, sir.
changing from 0 to t. G dash t, don't consider this. G dash t is what? G dash t.
Is a convolution and differentiation and shifted to tau.
Differentiation of this impulse, this step response, right? Differentiation of step response. So G dash t is the differentiation of step response, means impulse response.
We will get V dash t minus tau.
Huh?
We will get V t minus tau.
Vi t minus tau.
Tau.
Why do we get Vi t minus tau?
Because sir, impulse response. No, we are impulse. This is a phenomena of impulse that at impulse, where is the impulse occur, that value we have to put in multiplication of impulse signal into impulse.
Where exactly you are telling about? In this integral you are telling?
Yes, sir, in integral.
Integral, see, don't get confusion here. Simple. G of t, if you differentiate, what will you get? You will get
impulse.
I am telling
impulse
total
response.
integral, sir, 0 to t.
0 to?
T, total integral.
No, don't consider integral. I am asking only G dash t. I will tell you integral what it is later. But the G of t, if you differentiate, what you will get?
We get an impulse response. Sir.
Impulse response. Impulse response is transfer function, So, h of t. This is G of t. If you differentiate, you will get h of t. Okay.
Yes, sir.
And just substitute here in this integral. That integral can be rewritten 0 to t Vi of tau and into h of t minus tau
Yes.
and d tau. This is what we do to get output function. So this is the Duhamel's integral. Actually, for convolution also, Duhamel's integrals only are used. Actually, he has proposed for impulse functions only. But from that you can derive by simply using, differentiation of step response gives you impulse response. That by using that you can prove these two. So this is V out of t, V output of t, or this is V not t again. So can be expressed in terms of step response using this integral. That's it. Or this integral. Now we will use the latter, this one, to study here. what it is, how the impulse response will be. Now, this is about the step response, and using the step response, this is the measured step response, say, and using the step response, we can estimate output voltage for any given input voltage. Now, there is a concept known as response time. First, we will study these derivations, and from that we will get what the response time is. So, it's an important quantity in assessing the divider system or measuring system for impulse voltages. The response time is an important quantity. Now, let us consider our input as chopping on front a waveform, an input, an impulse waveform which is chopped on front, and front region, it is actually double exponential, and but however, in the front region you can consider it more or less linear. Do you agree?
Yes, sir.
More or less linear, right? So since it is linear, it can be written like this: a straight line passing through the origin. Vi of t equals to some constant s into time t. So v is equal to st. Okay, in the front region only. So after certain time, it is chopped, and then the waveform is becomes zero after certain time. But in the front region, it follows this Vi is equal to St. Let us observe what will be the output. We know from Duhamel's integral, just now we have seen how to obtain its output. So simple, this is the equation again. Duhamel's integral is written here. This is V naught t, output of t, and G of t into Vi of 0 plus. Vi of plus 0 means after t is equal to just 0, after immediately after 0. What is the value of VIT here?
0, because delay is there.
0 only. So, no, this is no delay. VIT is, please don't consider that step response. Step response is different. Now here my input is S into T. It starts from 0. But at T is equal to 0 plus also it is 0, because I have to multiply by 0 only. Right? S into 0. S into 0 becomes 0. Therefore, this part of the function is 0. And then plus integral 0 to t, Vi dash t minus tau. What is Vi dash?
Yes.
Simply constant. So it doesn't depend on t minus tau at all. Right? It is always constant. Irrespective of the value of tau, it always takes S only. Vi dash is equal to S. So that comes in this integral, and then since it is constant, it is taken out. You can see here. Now the rest of the function is G of t, d tau. So integral 0 to t, capital G of tau, d tau. Now G of tau is the step response, right? G of tau is the step response. Now I define small g of tau divided by n as capital G of tau. Why I define this? N actually is the ratio of voltages, steady state voltages from input to output. Just I will go back and then show you. So here actually whatever I get at the divider output on oscilloscope, will it be of same value as the input? Suppose my input is 1 unit, step function of 1 unit. Right? Say, step function of 1 unit. Then will I get the same value at the oscilloscope also?
No, sir, there will be a multiplication factor.
That multiplication factor is this N. Okay. So if I multiply the output function that is observed in the oscilloscope by capital N, I will get input. Okay. Input in the steady state. Steady state means, this region, in this region, still the output has not stabilized. But output is stabilized after this time, say. After the, settling time is given, tau s. So after this time, the output is stabilized, and this value should be compared to step input, unit step input, whatever is given. And this value, if I multiply by n, I will get the input, that is 1. So this is the factor. So my capital G of t now is defined as small g of t by n, or small g of t is capital G of t, in capital G of t into n, because you observe capital G of t is smaller. It is not unity. Its steady state value is not unity, very much less than unity. You are observing at the divider range, right? Oscilloscope. So it is very small quantity. So you have to multiply it with n to make the steady state value to unity. So this is how it is made. It's normalization. So therefore, s by n will come out, and integral 0 to 1 g of t will, g of tau d tau will remain in the integral. Now, what it is? Yes, a little bit simplification is done here. You can see. You can see here. This can be written as like this. Now I have taken n outside like this. So n into v naught t means simply multiplying the output by n, the divider ratio. So it should then follow the input, right? So here what it is done is this g of tau d tau is written as 1 minus g of tau d tau. Okay, and then a minus sign has come here. Now what is this quantity 1 minus g of tau d tau? It consists of two parts actually, 1 into d tau and minus of integral 0 to 1 d tau. So actually the second term corresponds to this only, exactly this second term. But this first term extra I have written. When this first term is written, I have compensated with by using p here. Does it match actually?
Yes, sir, it matches.
It matches because integral 0 to t dt, d tau is simply t. Okay, this first one corresponds to this only. The 1 corresponds to this only. Integral 1 into d tau, right? 1 into d tau. So integral 0 to t d tau is simply t. So it matches. Now t I have put here separately, and this is minus t, and then integral g of tau d tau. So this is just for making our analysis simple. It is done here. Now you can see, observe here. So since this is the quantity time t, this must also be a time, some time t, capital T of something like that, t of t, say. So it changes with time, right? Now, what is its maximum value? Whether, see, already g of t is normalized, right? Normalized, and g of tau, what is the final value of g of tau?
Unity.
Yeah, unity. So it is going to be 0 after some time. Do you understand? This 1 minus g of tau is going to be 0 after some time, and it will remain permanently 0 if the step input remains permanently there, and then this response becomes permanently g of t becomes permanently 1, and therefore 1 minus 1 is 0. So after some time this integral no more contributes any area. So therefore, up to certain time, it must have accumulated certain value that is defined like this. T naught. So integral 0 to infinity 1 minus g of tau d tau. This is defined as response time. Why is that so? What is it graphically? And you can see here, actually S of t, S into t is my input. Right?
Yes.
S into t is my input. For that input, some S into some capital T of tau is getting subtracted and you are observing at the output. S into capital T of tau, t. So this is what is getting subtracted with time, and after some time this capital T of tau is becoming a constant st naught. Right? So under steady state, your function will look like this, t minus some t naught for a long time, after a long time. So a constant time tau naught is to be subtracted from t, or yes, this function is a delayed function, delayed response. So as long as this t of t is changing with time, there are some oscillations. The moment this t of t becomes constant, then t of t becomes constant. Then after that, there will be no oscillations. Simply the output is delayed by certain time tau naught. So that is what is called response time. Let us see graphically what these are. Now you remember what is the definition of tau naught, t naught. T naught is 0 to infinity. Actually, you need not integrate up to infinity. After certain extent, then there will be no contribution because g of tau becomes 1 and then 1 minus 1, 0. Therefore, you need not integrate up to infinity in practice. In practice, it can be measured easily. That's why this quantity came into picture, and it has some real significance to the system's response or characteristics. Now you can see this response time times and step response. Now you can see here, this is the step response after this is capital GT, and then if you multiply it by n, it will become small gt. Now here it is given small gt, this is small gt multiplied by n, of course. So now this is the response, step response. Now let us see the definition of tau naught. So this is the definition of tau naught, t naught, sorry, not tau naught. T naught means response time. So what it is actually, you can see this is 1. Okay, and then 1 minus g of t d tau. So what it is actually?
Area, sir.
Huh?
Area.
Shaded area, right? Shaded area in the figure. The shaded area in the figure, 1 minus g of tau d tau is the shaded area, this one. And this one. And this one. This one. Like that. So this is what it will become. What is T naught? T naught is T1, this area, minus T2, this area, and plus T3, this area, minus T4, like this. It continues, but it can be measured after certain time. The area will be negligible. Now you can see there is a delay. This, what is this area actually? If this is TDE, tau DE,
Rectangular area, sir.
delay time. No, this rectangular area. What is that area?
TD into 1.
That's TDE only.
Yes, sir.
Okay, so this area, this rectangular area corresponds to delay time TDE. Okay, and then the rest of the area, including this, contributes to the response time tau naught in this fashion. Tau naught equals to T1 minus T2 plus T3 minus T4. Like that, this series continues until you observe something. So this quantity, this impulse response, this step response can be practically measured. Of course, there are limitations, but yet you can obtain this quantity, this T naught, experimentally. So that is one advantage of this system. Now let us see. In terms of this impulse response, let us see. Yeah. Now response times, chopped impulse response. So the same things what they are here that we will observe. Here you can see Vi of t minus n times output. Input minus n times output. Same whatever we have used there. So this is nothing but st will go. See in the previous one of the functions we have seen v naught t is written as, just I will go back and then show you. V naught t is n into v naught t, you can see this is st, right? This st will go and the remaining function will remain if you subtract it from the input. Input is st, right? That's why. So input is st and nv naught t is also having the st function and the remaining one is here. So simply this is s into t naught. Okay, for t greater than ts after settling time, this integrated on t to more than t of s. T of s itself, the g tau will become 1 and then after that it doesn't contribute. So infinity and then t of tau of s will yield greater than tau of s will yield almost same value. That is why this constant will turn out to be t naught only, s t naught. So the difference between input signal and n times output signal is s into t naught. S into t naught. Then again, what is delta V? Delta V is defined like this here. This is delta V. You can see Vi of Tc, so exactly at Tc. So let me first explain. So this is our input function. What it is? What is its mathematical equation? What is its mathematical equation? This one.
T only, sir.
Linear T only. So T only.
This is
divided
input.
by T. So slope.
This is input Vi. Is equal to?
1 upon Tc into T.
No. S into small t.
Yes, into T.
Input function. And it is chopped at t is equal to Tc. Okay.
Yes.
And for this input function, we have obtained output function n into V naught t. See, I cannot compare simple V naught t. I have to compare n into V naught t because the input and output will be having this dividing ratio, right? Impulse dividing ratio, impulse divider ratio. So that is why output is multiplied by n and then compared. So this is exactly the output. So here you can see initially it has oscillations Then after it is chopped at TC, so then here the waveform comes like this. Actually, there is an initial delay TDE. This is observed in step response also. So here that delay will reflect like this. But due to that delay, this function will again continue after TC, after chopping also, for this delay time TDE. But it will not reach the maximum. So because this is the reason. Delta V, this is mathematical explanation here. What happened? Pen is not working. So this is delta V equal of TC. This is TC, right? So TC at VI means this value, VI of TC. And then N times V naught of TC plus tau DE. So this is tau DE, delay time. And then this is TC. TC plus tau DE is this instant. TC plus tau DE at this instant. Now at this instant, the value of output is this one. So the difference between this and this is delta V. It is the steady state error. Okay. Now what it becomes, you can see. Now VI of TC, N minus N into V naught TC plus TDE is ST naught minus TDE equals to ST. How it is? Let us see. What is ST naught? ST naught is this quantity, vertical quantity at any after settling time. After settling time, ST naught is this gap. ST naught. It won't change after. Do you understand? Shall I repeat?
Sir, ST naught will be the error for the output till TC, right?
Till
Tau. Like ST
Till
naught
what?
will go on
See,
until when we are going to take this difference?
ST naught is actually, you can say, as dynamic error. Means if you observe at a particular instant of time, at that instant of time, and this instant of time should be after settling time actually. So
Okay.
if you are still increasing the input, you observe the output to be less than by this quantity, ST naught. That's what I am saying.
Okay. Yes,
So
sir.
this is the, suppose this is the settling time somewhere here. This is the settling time. After this, if you observe, this vertical difference is there, na? Okay. This is ST naught.
Okay.
But what happens? The signal will not stop at TC. Until TC, you can observe this ST naught is constant.
Yes,
But
sir.
the output signal still continues. And it reaches it until TDE, it continues. So it reaches a certain value and then it stops. So this is defined as ST.
Okay.
Now this vertical and horizontal relations we have to obtain here. If this is ST naught, what is this quantity? This triangle. This is exactly T naught. Do you agree? This is ST, okay? And the steady state value I'm talking, the steady state value is ST naught. Then this quantity, sorry, ST minus T naught. The steady state quantity is ST minus T naught. So this is ST minus T naught and this is ST. Okay. Then therefore this time is T naught. Do you want me to go back? Okay, I will go back once. A little bit tricky, but you have to understand this, otherwise. See, n times of output voltage V naught T is given by this integral. In this integral, this can be written as S into T minus some T of T. Okay. Now this T of T, I told you, becomes constant after certain time due to the reason that this integral becomes constant due to the reason that GT becomes 1 and after certain time there is no contribution of this integral. So therefore S into T minus T naught after settling time, after steady state. In steady state, S into T minus T naught. What is this? This is simply output function. Output function is S into T minus T naught. It is a delayed function, that's what I told you. Now go back to this function, this slide here. Now you see, this is what I am referring to. This is input function. Input function is given by simply S into T. And this is output function. Output function is given by S into T minus T naught. Right? So if this is S into T, this is S into T minus T naught. This is after settling time, please remember. After settling time, well beyond the settling time. Otherwise, the difference will go on changing here dynamically. Okay. So after settling time, what happens? This becomes S into T minus T naught. Therefore, this difference, the dynamic difference at any instant of time, this is S into T naught only, this dynamic difference, S into capital T naught. If this is S into capital T naught, that corresponding difference in times, okay, if you look at this triangle, this is simply T naught. Because this is T, this is T, this is T naught. So the time correspondence is this function will be T naught seconds. After T naught seconds, it will come the same position. Therefore, this value is T plus T naught. Is it clear? Okay, think carefully. If you do not understand after rethinking again, you again ask me if you have any questions there. Because you have to synchronize with my, with whatever I am telling, then only you can understand. So this time T naught, the gap between this from this instant to this instant is already defined like this. Now you can see there is a delay. If you subtract that delay, this delay actually normally neglected, because see, how does it matter if there is a delay in recording in the oscilloscope? Suppose you are getting recording in the oscilloscope, the step or ramp or whatever, some input is applied in the input, but you started recording at some instant. Just you redefine your origin, t is equal to 0 at that instant. So it doesn't matter, that delay is immaterial. That's why this delay TDE can be ignored or neglected, and we concentrate on the remaining time, this delay. So that delay is defined like this. How is it defined? Just you observe only the initial, the lower bound of the integral is changed to TDE. Earlier it was 0, now it is changed to TDE. Simply, it is subtracting this time TDE from the time T0. That's what will happen. So this is what will happen. S T0 minus TDE, tau DE. So this is what is the response time. Okay. So this response time, new response time, is ignoring the delay tau DE. But T0 is also specified, and T is also specified, or can be measured experimentally, and then these quantities can be specified for understanding the transfer characteristics of the measuring system. Now, relative amplitude error is defined like this: delta V divided by STC. STC is this magnitude actually. S into T is this waveform, right? So STC corresponds to this peak. So we are simply dividing this delta V divided by the peak voltage of input. Then that corresponds to simply T by TC. What is T? T is defined by this, the time, the response time ignoring the initial delay is defined as T. So T by TC is relative amplitude error. So we can specify for a given dividing system a value of delta, a value of T, and a value of T0 can be actually experimentally measured, and then the system may be characterized using this. Of course, there are certain drawbacks for this criteria, because linearly rising high voltages are difficult to generate, and it is difficult to confirm this linearity by measurement. See, normally the rising voltages may have lot of oscillations, and sometimes due to ringing, the measurement, the T may become even negative. So it is difficult to get linearly rising high voltages, but step voltage can still be applied. So step voltage can still be applied and then measured, but of course there are limitations for that also. Just I will read it out. Now, low or negative values are likely to be achieved by excessive ringing or large overshoot of the step response, due to large low or negative values of T or T0 or T are likely in the responses actually, due to large overshoots sometimes. So this is a difficulty here. And then actual integration of a measured unit step response must be carried out carefully. See, when you measure experimentally, what is the difficulty? You will be getting a step response, but you have to wait sufficiently longer time to ensure that your final value GT, you have to fix it to 1. So you have to calibrate the signal in such a way, whatever you get the value at the far end of the waveform, that you have to fix it to 1, because GT equals to 1, right? So after fixing this, then you have to integrate 1 minus GT to obtain this T0, etc. And then actual unit step response cannot be measured for the real layout of the HP measuring circuit due to large test objects. This is one fundamental difficulty actually in obtaining this, because the test object size is huge. Sometimes you may be testing very big cable systems of long length, and then its height must be huge, depending on the voltage level, terminating terminators, what they are terminators, will have huge height, and then you have to apply a unit step function there. So how to apply? There are complicated difficulties in applying the step input at that for that large heights and all. And then this is one of the difficulties. But of course, real layout is not used, but some standard layout has been suggested in the standards, which can be used to measure the step response. But in spite of these drawbacks, the concept of response times has the biggest advantage related to its computation, as T naught or T can be calculated even for a very sophisticated network without even GT, without even measurement. Actually, if we know, if we have an equivalent circuit, however complex it is, for example, we will see for the dividers, it is possible to analytically estimate the value of T naught and T, and even computational programs also can be used to just what we have to do. We have to obtain a step response of the system. After obtaining the step response from the equivalent circuit, you measure this, what is 1 minus GT and all. That T naught can be computed, and then from that T can be computed if we know the delay and all. So there are advantages of these specifications. Actually, the standards do recommend using these specifications for impulse circuits, impulse dividing circuits. So after this, okay, so this lecture is over here. We'll continue in the next lecture. Actually, this topic is not completed. Maybe another one lecture we may finish the topic. So you have any questions here? Of course, it is a little tricky to understand that. You have to carefully watch the waveforms, and then whatever is told, you carefully observe. And if you do not understand, and if there is any doubt, you can always ask me. Even after this lecture also you can ask me. It's not. But now if you have any doubts, you can quickly ask me. Hello?
Sir, by doing this, taking the transfer function and obtaining the response, are we trying to obtain the stability and all of the measuring system? What is the basically significance of doing this?
No, not stability. Stability, the system is stable only. It's not a big problem. But we are more interested in observing the measurement errors. See, you are ultimately saying something about the input function, right? If your output, whatever you have measured, deviates from the input in a big way. For example, input there are no oscillations. Output you are getting oscillations at the oscilloscope, and you wrongly conclude that these oscillations are actually applied across the test object. Then that is wrong, right? So our main objective is to understand the errors in the output voltage, whatever we are measuring. So for that, how to characterize the system? You have an impulse measuring system, and you have given an output to me, and then this is the waveform you said that is applied to the test object. Then how should I believe? You have to supply me what is the what are the characteristics of your measuring system. So for that you need to give me the specifications. So this is my T naught, this is my T, this is my delta. So like that you have to specification so that I understand that this is the measured value. So the actual value can be, actual voltage can be like this. At the most, this much error I can expect. Like that, people will understand. That's what is the purpose. It's not stability. The system is stable only.
Okay, sir. Thank you, sir.
Sir, this is for French chopped, right?
Huh? This is for
This
front
is
chopped, but it explains in general what is T naught and what is see actually oscillations. What are the differences? This is the fundamental difference. Okay, these oscillations,
yes, sir.
and after certain time, definitely input output follows the input.
Yes,
Okay,
sir.
but there is a maximum peak error. That error can be that also will depend on the at the time of chopping and all. Okay, so
Okay.
that can be evaluated like this. For example, if you have chopped it 1 second, what is the expected error? What is like that? The peak error we can understand. That's what it is.
Okay. And for back chop also we'll have a similar analysis.
For
This is front chop for back chop, like where
yeah.
chopping.
It will continue. See, after this time, the response will simply follow it, right?
Yes,
So
sir.
initially, these oscillations corresponds to the the system response. After that, output follows the input, and whenever it is chopped again, there will be certainly like this, a waveform like this will come. So there, what is the amplitude error that can be calculated?
Okay, sir.
Sir, in tail chop, we have to take a decreasing linear wave, no, sir?
Huh?
In tail chop,
In
tail chop, sir.
tail chopped. Okay.
Yes, sir.
Huh.
Here is the rising and goes to the unity for the tail chop from unity and it goes down, no, sir? Linearly. Reverse
You
process is
can,
there.
yeah. You can assume linearity, but it is, of course, double exponential. But the system is characterized by these delays. That's it. Characteristics of the system you should know.
Yes, sir.
Okay.
Yes, sir.
Okay then.